Hello students, and welcome to lesson 19, all about complex numbers. In this lesson, we will learn how to add and subtract complex numbers, what a complex number is, how to multiply and divide complex numbers, and how to simplify powers of I. So now, the question you should be asking is, why do we need complex numbers? Okay, we already have real numbers, aren't those good enough? And well, the answer to that is quite simple. We need a solution to the equation x squared plus 1 equals 0. And if you don't have complex numbers, you don't have that solution, okay? So we have to go into a imaginary field where we actually do have an answer to that. All right. When you go deeper into mathematics, there are an entire branch of mathematics, probably several branches really, that focus on complex numbers. And one such thing is the Mandelbrot set, which comes out of fractal geometry. So that's pictured here on the left. I encourage you to scan that QR code and watch the video. Essentially what happens is as you zoom in on the picture, it repeats itself and becomes more and more complicated as time goes on. It's really just fun imagery, but there's a lot of math behind it, and it's something that we have no time for in this class, and is really a graduate level concept in mathematics. But if you at all find that image on the left interesting, I encourage you to scan that QR code and see a little YouTube video that it doesn't teach you anything. It just zooms in and in and in on the Mandelbrot set. All right, so now what is a complex number? A complex number consists of a real and an imaginary part, and its complex form looks like a plus bi, where a is the real part and b is the imaginary part. The imaginary number I is defined as the square root of -1. So if you're wondering where any of this comes from, we previously said that square roots of negative numbers did not exist. Well, they don't exist in the real numbers, but they do exist in the imaginary and complex numbers. And so what we did is we defined this letter I as the square root of -1. That way we could continue doing mathematics on things that previously we would have to just stop at. All right, so now we can write the square root of any negative number as a multiple of I. So for instance, the square root of -49, 49 or -49 is 49 times -1. So we can break this up as square root 49 times square root -1, where the square root of 49 is 7, and the square root of -1 is I. So we can just write this as 7I. What you really need to take away from this is when you square root a negative number, the negative sign comes out as the letter I, and then you just act as normal for the rest of the square root. So 49 you square root to get 7, but it was that negative sign that gave us this I in the back. All right, so let's see a quick example of that. If we want to express 7 plus 2 square root -36 as a complex number, we're going to write 7 plus 2 and then square root -36. The negative sign becomes an I, and square root 36 is 6. So all we do is square root the 36 as normal to get 6, but the square root of this -1 is this I right here. So then we simplify this to just be 7 plus 12I, where all you do is treat I like as a variable. 2 times 6 is 12, and we leave that I attached in the back. All right, adding and subtracting complex numbers. As I just said, what we're going to do is treat the letter I as a variable, and we're just going to combine like terms. So if we want to add 21 minus 8i plus 10 plus 24i, just pretend the I is the letter x and treat it as if you were combining like terms. So 21 plus 10 is 31, and -8i plus 24i is positive 16i, where all we did was combine 21 and 10 to get 31, combine -8i and positive 24i to get positive 16i. Nothing else to it. When you subtract, just like normal, you have to make sure you distribute. So for number 3, 21 minus 8i minus 10 plus 24i is the same thing as 21 minus 8i minus 10 minus 24i, where I distribute that negative sign to both things inside. And then we just combine like terms. 21 minus 10 is 11. -8i minus 24i is -32i. Okay, now we're going to multiply complex numbers. When you multiply complex numbers, there's really only one thing you need to remember, and that is that I equals square root negative 1. Because of that, okay, because I is square root negative 1, that means I squared equals negative 1. Because notice if we square both sides of this, negative 1, its square root squared, the square root and the square cancel to just give us negative 1. So I equals square root negative 1, which means I squared equals plain old negative 1. When we multiply things out, we multiply out as if I was a variable, just treat it like an x, but I squared will be equal to negative 1. Okay, so for number 4, we're going to distribute negative 4i to 6 and 3i. Negative 4i times 6 is negative 24i. Negative 4i times 3i is negative 12i squared. So that felt normal. All we did was distribute as if it was an x. But now we replace I squared with negative 1. Okay, so negative 24i minus 12i squared. That I squared gets replaced with a negative 1. And this becomes positive 12 minus 24i. Where notice I wrote the positive 12 in front because standard form of a complex number is a plus bi. All right, so one key there is to make sure that we replace I squared with negative 1. And the other key is to make sure that at the end of the problem, we write it in standard form, a plus bi. For number 5, now we have two binomials that we have to multiply. So we're going to multiply 10 times both things in the second set of parentheses, and 8i times both things in the second set. So 10 times negative 2 is negative 20. 10 times 12i is 120i. 8i times negative 2 is negative 16i. And 8i times 12i is 96i squared. So now we need to make sure we combine like terms in the middle and that we replace I squared with negative 1. So we're going to get negative 20 plus 120i minus 16i is 104i. And then 96i squared becomes negative 96 because I squared is negative 1 times positive 96 is negative 96. Now we put together the negative 20 and the negative 96 to get negative 116 plus 104i. All right, if you can do that, then the next part's not too bad, even though it seems a little complicated what we're about to do. All dividing complex numbers is multiplying with a couple extra steps. So dividing complex numbers is actually the same as when we rationalize denominators. Before actually dividing, we first must get rid of any imaginary parts in the denominator by multiplying numerator and denominator by the complex conjugate of the denominator. And the complex conjugate of a plus bi is a minus bi, where all we do is change that plus to a minus. When we do this, because we're multiplying conjugates together, we get difference of squares. Okay, where notice we get a squared minus abi plus abi minus b squared I squared. But the middle two terms there, negative abi and positive abi, go away. And because I squared is negative 1, negative b squared I squared just becomes positive b squared. So we can skip a couple steps when we do the denominator and just go straight to a squared plus b squared. So for number 6 here, we have 1 plus 4i over negative 7 minus 4i. We're going to multiply top and bottom by the complex conjugate of the denominator, which is negative 7 plus 4i, where all we do is change the sign on the I part of the complex number. In the numerator, there's no shortcut. We have to multiply it out. So we do 1 times negative 7 is negative 7. 1 times 4i is 4i. 4i times negative 7 is negative 28i. And 4i times 4i is 16i squared. In the denominator, though, there is a shortcut. When you multiply complex conjugates, you get a squared plus b squared, where in this case, a is negative 7, so negative 7 squared is 49, and b is 4, 4 squared is 16. So in the denominator here, I just have 49 plus 16. So we can simplify that denominator real quick. That adds up to be 65. And in the numerator, we can combine like terms. So we have negative 7 minus 24i, and that 16i squared becomes negative 16. So then we can combine like terms again to get negative 23i minus 24i. Oops, sorry, a little typo there. Negative 23, no I, because just negative 7 minus 16, then minus 24i. And this is all over 65. Now, usually it's good to write it in standard form. So instead of leaving this as one fraction the way we wrote it, what you want to do is break it down to negative 23 over 65 is the real part, and negative 24 over 65i is the imaginary part. Not completely necessary. It doesn't really make it look any nicer, but it does put it back into that standard form, a plus bi. All right, one last part of this thing, powers of I. So the powers of I are cyclic, meaning they come full circle. So if we look at the first 5 powers of I, we have that I to the power 1. Well, that's just I, okay? That's square root negative 1. We've already seen that I squared is negative 1, because when you square the square root of negative 1, you just get negative 1 back. But now let's keep going. I cubed is I squared times I. I squared is negative 1. So I squared times I is actually just negative 1 times I. So that's negative I. All right, so I cubed is negative I. I to the power 4 is I cubed times I. I cubed is negative I. And so negative I times I gives us negative I squared. But negative I squared, well, I squared is negative 1. So this is just negative 1, which is positive 1. And then if we keep going, I to the 5th is I to the 4th times I, but I to the 4th is just 1. So 1 times I is just I, and notice that means we're back to where we started. So I to the 5th is the same as I to the 1st. And that pattern will keep going every 4 you repeat yourself. So what this means is that we can simplify large exponents on i's by just dividing by 4 and seeing what the remainder is. So for example, in number 7 here, I to the 22nd is going to be equivalent to I squared. Now, why do I know that? Well, all I did was do 22 divided by 4, where I used the number 4 specifically because it takes 4 powers of I to repeat yourself. Okay, 22 divided by 4 is 5 with a remainder of 2. So this remainder of 2 is what becomes my new exponent. Okay, so now I can write that out in a little bit more detail of why is this true. So let's add an extra step real quick. I to the 22 is really I to the power 4 to the power 5 and then times I squared. Now why is that true? Well, I to the 4 to the power 5, you multiply the exponents. 4 times 5 is 20. So this first part is I to the 20. And then I to the 20 times I squared, you add the exponents, so you get back to I to the 22. But why do I want to write it that way? Well, I to the 4th, notice the chart above, is just 1. So this is now 1 to the 5th times I squared, which is just I squared. Okay, so we can skip all those steps and just say that I squared, where 2 is the remainder when we divide, is what I to the 22nd simplifies to be. So all you need to do to simplify powers of I is divide by 4 and put the remainder as our new exponent. All right, but we're not quite done yet because I squared is negative 1. So in the end, we can say that I to the 22 is just equal to negative 1. If we try that again for number 8, we have I to the 75. 75 divided by 4. Put a 1 there, subtract. We get 35. 8 goes into 4 goes into 35 8 times, subtract a 32, we get a 3. And so this 3 is our remainder. So we can then say that I to the 75 is equal to I cubed, and I cubed, referencing up above, is just negative I. So I to the 75 is actually just negative I, and I to the 22 was negative 1. And that's all I have for you on complex numbers. Thank you for joining me. See you guys next time.